Hello, everyone, and welcome to Lesson 3 to 5, titled Introduction to Cryptography. In this lesson, we'll take our first steps into the fascinating world of cryptography, the science of securing information so that it remains private, trustworthy, and tamper-proof. You may not realize it, but cryptography touches your life every single day. When you unlock your phone, log into a website, send a message, or check your bank account, cryptography is working quietly in the background to keep your information safe. So, what is cryptography? At its core, cryptography is a method for transforming information in a way that makes it unreadable to unauthorized people. The word itself comes from Greek roots that mean hidden writing. But in today's digital world, cryptography does far more than just hide messages. It ensures that data can only be read by the right person, that it hasn't been altered, and that it truly came from the person who claims to have sent it. Let's begin with the 4 core goals of cryptography. These are confidentiality, integrity, authentication, and non-repudiation. Confidentiality means that only the intended recipient can read the message. This is what most people think of when they hear the word encryption. Imagine writing a note and locking it in a box. Only someone with the right key can open the box and read the note. In digital terms, encryption locks the data so that no one else can understand it. Integrity ensures that the message has not been altered. Think of a sealed envelope. If the seal is broken, you know the letter might have been tampered with. In cryptography, there are ways to check whether data has been changed, even slightly. This is especially important for things like financial transactions or software updates. Authentication is about knowing who you're communicating with. For example, when you receive a message, you want to be sure it really came from your friend and not an imposter. Cryptographic systems help verify identities online, just like showing an ID card in person. Finally, non-repudiation means that someone cannot deny their involvement. If a person signs a digital document, cryptography can prove they did it. This is crucial in situations like contracts or legal agreements. Now that we understand what cryptography aims to do, let's look at how it actually works. There are 2 main types of encryption, symmetric and asymmetric. Symmetric encryption is the simpler of the 2. It uses the same key to both lock and unlock the message. Imagine you and a friend each have an identical key. You use your key to lock the message, and your friend uses their copy to unlock it. The challenge here is that both people must have the key ahead of time, and they must keep it secret. This system works well when both parties already trust each other and can share the key securely. For example, symmetric encryption is often used inside closed systems like secure databases or corporate networks. The second type is asymmetric encryption, which is also called public key encryption. This method uses 2 keys, a public key and a private key. The public key is shared with everyone, while the private key is kept secret. Here's how it works. If I want to send you a secret message, I use your public key to encrypt it. Once encrypted, only your private key can decrypt it. That means anyone can send you a secure message, but only you can read it. This solves the problem of key distribution, because you don't need to secretly share a key ahead of time. Asymmetric encryption is used in many places online. For instance, when you visit a secure website, one that starts with HTTPS, your browser is using asymmetric encryption to establish a safe connection with the website server. Another important concept in cryptography is hashing. A hash function takes input data and transforms it into a fixed-length string of characters, which is usually a combination of letters and numbers. This string is called a hash or hash value. What makes hashing powerful is that the same input always produces the same output, but even the tiniest change in the input creates a completely different hash. For example, if you hash the word hello, you might get one value. But if you change just one letter, like typing hello with a lowercase h, the resulting hash will be totally different. Hashes are not meant to be reversed. That means you can't take the hash and figure out what the original input was. This is different from encryption, where you can go back and forth between the original and encrypted versions using keys. One of the most common uses of hashing is in password protection. When you create an account online and choose a password, the system stores the hash of your password, not the password itself. Then, every time you log in, the system hashes what you type and compares it to the stored hash. If they match, you get access. This way, even if the database is hacked, the actual passwords remain unknown. Hashes are also used to verify file integrity. For example, when you download software, the website might provide a hash value. After you download the file, you can hash it yourself. If the hash matches, you know the file hasn't been tampered with. If it's different, something may be wrong. Now let's talk about real-world applications of cryptography. You've probably noticed a small padlock icon next to a website address in your browser. This means the website is using HTTPS, a secure version of HTTP. HTTPS uses encryption to protect any information you exchange with the site, such as login credentials or payment details. Digital signatures are another common application. These are like handwritten signatures, but in digital form. They use a combination of hashing and asymmetric encryption to prove that a document was created and signed by a specific person. If the document is changed in any way after signing, the signature becomes invalid. This is used in everything from software distribution to legal contracts. Encrypted messaging apps also rely on cryptography. Apps like WhatsApp and Signal use end-to-end encryption. That means only the sender and the receiver can read the messages, not even the app provider can access the content. Another important use of cryptography is in virtual private networks, or VPNs. A VPN creates a secure tunnel between your device and the internet, encrypting all the data that passes through. This is especially helpful when using public Wi-Fi networks, where your data could otherwise be intercepted. As we can see, cryptography has become a cornerstone of our digital lives. But it's important to note that cryptography is not infallible. Weak encryption algorithms can be broken, poor key management can lead to exposure, and human error can bypass even the strongest systems. That's why cryptography must be combined with good cybersecurity practices. Choosing strong passwords, using two-factor authentication, and keeping your software updated are just as important as the encryption itself. Let's take a moment to review the key concepts we've learned. First, we define cryptography as the science of protecting information. It supports four main goals: confidentiality, integrity, authentication, and non-repudiation. We discussed symmetric encryption, which uses the same key for both encryption and decryption, and asymmetric encryption, which uses a pair of public and private keys to secure communication. We then explored hashing, a one-way process that turns input data into a fixed output, used in password storage and file verification. Finally, we looked at how cryptography is used in the real world, including secure websites, encrypted messages, digital signatures, and VPNs. Before we close, I'd like to leave you with a thought. Cryptography may seem like a complex, abstract subject, but it's actually one of the most practical and empowering tools in modern life. It allows you to trust the messages you send, the websites you visit, and the services you use. As digital citizens, understanding cryptography is like knowing how to lock your door, fasten your seatbelt, or verify someone's identity. It's a basic skill for a secure and informed life in the digital age. Thank you for your attention during this lesson. In the next session, we will explore how these cryptographic tools are used in real-world scenarios, from government systems to personal devices, and learn how to evaluate the security of digital environments. Until then, stay safe, stay informed, and remember, every secure message, login, and transaction begins with the principles of cryptography.